Yeah, hi everyone. Welcome to Numpy 4. So, in this lecture, we'll be discussing about these topics. So, broadly speaking, there are only three of them. So, the first one is about shallow versus deep copy. So, this is about how Numpy stores the data in the memory locations. The second one is about array splitting. It's about how you can split a single array into multiple subarrays. Then the third one is about array stacking. So after you split, like maybe you want to merge the arrays together in different ways. So that's about array stacking. So this is all there is to it. So let's begin with the first one. Shallow versus deep copy. So basically, Python reuses the object. So in Python, everything is an object, and Python likes to reuse objects as much as possible. And it's just for performance and efficiency. However, many times you will many times there will be a need to duplicate the data when we are making some transformations or something like that. So that is where this concept of shallow and deep copy comes, where Python and NumPy make use of these concepts to do things appropriately. So there are two methods. One is view and the other is copy, that are inbuilt in NumPy. There is something called deep copy as well, but that is part of the copy library, which we will see. There is an exception. There is a scenario where copy doesn't work. That's when we'll have to use deep copy to duplicate that data. So the first thing we'll look at view. So view is basically it's just a view of the original array. It's like a reference of the original array. So let's say we create an array. So we have 9 elements. Now if we print this, we have this array. Now suppose if I update the first value, the first element at index 0 to say 89. So if you see, the array got updated because we are directly operating on this array. Now suppose I do an array dot, I create an array2 equal to array dot view, and if we print the array2, the array2 is also the same because we are actually referencing it. And the way to check if we are referencing it or not is you can do something like if I update array2's first element to say 77, and then I print the first array. You see, the first array got updated. The first array's first element got updated to 77. So that's where the reference comes in. So we can check if these both arrays are sharing the same memory using a method called np.shares memory r2. and it says the answer is true because those both are sharing the memory. If you look at the documentation, determines if two arrays share memory. So that's what that's what view is about. Now let's look at copy. Let's take the same example. Now instead of view, we can call the method copy. Now if I do a copy and then I update the second array's first element to 77, right? Okay, before that I guess let's just see if the data is correct or not. So we have 0, 1, 2, 3 and array 2 is also 0, 1, 2, 3. So now if I update the second array, and if I print array 2, if I print array, the first array remains intact. The second array changed, got updated. Now if you check the same thing in shares memory, it says false. So that is how it is. So that's how view and copy work. So if you want to duplicate the data and you don't want to update the original one, you can use this handy method. Let's see. I guess we discussed the theory in the first lecture regarding how Numpy stores the data in the memory locations. Let me just refresh that a bit. So basically, Numpy stores the data in contiguous memory locations, meaning one after the other. So if you consider this as a memory strip, each block is a memory block. It has certain it has a certain value, let's say 4 bytes or something like that. The Numpy, when it stores the data, it stores it in one after the other locations, contiguous memory locations. That's what it means. But Python does not do that. Python, since Python lists can accept heterogeneous data, meaning multiple data types. A list can have, so Python list can have like an int or a booleans or a strings or even lists of lists or even maps, sets or maps. So these are not stored in contiguous memory locations. These are stored in some RAM. So this can be here, this value can be here, this can be in some other location, but that's not the case, since Numpy only takes single data type lists or arrays. All the elements will be stored in contiguous memory locations. So if you have 1, 2, 3, 4, they will exactly be in these locations, and that's where it internally optimizes. It has this. It has some algorithms internally to speed up the performance. So now the reason why we are discussing this is because there is a particular scenario where copy doesn't work. But before that, let's see, something slipping my mind. So we discussed view versus copy. We checked both memory locations, method that use either of these. What's that use? Either of these. Right. So yeah, I was forgetting this one. So what operations in Numpy use this? Use a copy or use a view. So suppose we have slicing. So array slicing, this particular slicing uses view. It does not, so we discussed, right? NumPy reuses the data as much as possible. It does not like creating duplicates. So operations like slicing or even what else does so reshaping of a let's say we have a 3x3 matrix, and if we we have a 1D matrix and we reshaped it to 3x3, that is also it also creates a view. It does not duplicate the data. Even transpose as well. So you have a row column thing and it creates a column row. Since the elements are essentially the same, it does not like creating duplicates. And so there are some other methods as well which use views, but these are the common ones that create views. And if we see copy operations like arithmetic operations, like all so if we did vectorization kind of thing, array times 2 or array plus 2 or any sort of arithmetic, or even if we supposed flattened a list, the essential structure got changed, right? So even that creates a copy. It creates a duplicate data because all complicated operations it will create a new structure. So it stores them in separate memory locations. What else does it create a copy of? Arithmetic operations, flattening the list. Masking as well. So we have filters, right? Filtering or masking. So if we take array and then we say array less than 2 or something like that, all these scenarios NumPy creates a copy. Now coming to the exception, there is a scenario where a copy method fails. So array.copy fails on object arrays. So basically, if we have, suppose create a new array, np.array, and I create something like, I want an integer, I want a boolean, I want another list. Suppose I want another list within this list, and I want maybe some sets as well, right? So this is a heterogeneous list which is actually not supported in NumPy, provided it is generally not supported, but if you specify the data type to object, since all the everything is an object in Python, all these things are essentially objects. So it is technically a homogeneous data array. So NumPy actually supports this, but the list gets converted. The NumPy special features will not be available on this, like features like what is it called, broadcasting won't be available. You will not have the vectorized operations, like you cannot do stuff like array times 2, because now is different type of data, right? So I mean it won't know what to do with how to multiply, how to square or how to multiply this thing with an integer. So vectorized operations are not possible. You won't have broadcasting, so it will not automatically adjust the array to make it compatible with another array to perform arithmetic operations. So that's not possible. Then what else? I think you will not you will lose a lot of NumPy features when you use object arrays in NumPy, and it's in fact significantly slower than vectorized operations. Obviously, even if you take the entire array, even if you take this as strictly an integer array, but if you add the data type as an object, it is actually significantly slower than traditional NumPy array, where you can perform this vectorized operation. So suppose you do an A range. Let's take 10,000 elements. Standard example, we specify the data type. Right. So let's do a time it on this one. Percent time it. Let's check the usual example. So this took 334 microseconds. Now if we do this on traditional NumPy array without using the object data type, five microseconds, approx 5, right? So that's enormous difference. And as usual, pure Python lists are much slower. So if we so def my for x in array. So that is 592 microseconds. So that's the performance comparison, and as you can see, it drastically reduces the performance if you use object array. But what you gain is that it behaves like a normal Python list. So you can perform standard Python operations, like standard Python list operations on it. So that's the catch there of using object arrays, and the real catch is you cannot use copy on object arrays. So suppose I take this, let's take this object array, and if I do a array.copy, call it array2, and I do array.copy, and if we check np.shares memory, it says false. So the original and the copy give shares memory as false, which means it is recognizing both of them as different, and that is because the outer structure of the first array is actually copied. So it copied one, let's say it copied true, but it did not, it just copied, just think of it as an empty array. It's still referencing the inner elements to the original values, so to the original memory locations. It's not creating duplicates of these inner elements, which is why you need a deep copy for this. So to give you an example, so suppose if I do np, so sorry, not np, if I change the first element of the array in array 2, let's say I call it 898, and then I print array 2 got updated to 898. Let's print array 1. Array 1 remains the same. But if I suppose do if I try to update this list, So 0, 1, 2, so that's the second element. And if I change the first second element, which is the list, and the first element within that list, if I change the first element within that list to 898, if I print array 2, you see the array 2 got changed to 898, and if we check array 1 as well, array 1 is also changed. You see that? So that is where we need, that is why we need a deep copy. Now if we create something called, let's create a deep copy of this. So we import copy, that's the library we need, and we do array 2 equal to copy dot deep copy, and then we pass the array. Okay, now if we print, let's check the original array. The original array is still the same. Now if I suppose update array 2, we take this operation, and then I try to print array. Let's print array 2 first. Array 2 got modified. You see here the item got updated to 898. Now if we check array 1, that remains the same. So now if we, again, this will still show as false because they are not sharing the memory, but right now this is true deep copy. So that's how you can create duplicates of the data. Let's see, we did speed comparison. What else? Yeah, so let's look at the memory, how the reuse happens in Numpy. So if you look at the, so we can check the memory locations. So Numpy internally uses CPython for creating lists, and it supports values from minus, I think it's -5 to 256 if I'm not wrong. So if it goes anything beyond these values, it automatically creates allocates new memory location. But if it is within these two values, if the value is within -5 to 256, the Numpy keeps reusing the same value. So suppose if I give a equal to, let's say 556, and if I set b equal to 556, and if I try to say compare the IDs, ID of A invalid, oh okay. So this is the memory location of A where this 556 value is stored, and if we look at B, let's print them. These both are pointing to different addresses. Now if I set B equal to A, then both are in same memory locations, because it's essentially taking that value from A. Now in Numpy, if we look at the memory allocation, okay, let me try to bump this up to 1200. It is still the same for this, is because this is normal Python. But if we look at Numpy, since Numpy uses C has this limitation, -5 to 256. This is standard Python. If we look at say array equal to np dot a range 9. Okay, not a range. Let's take a array. We have let's give 2000. Let's take 300 itself. We don't have to go that far. 300, 4300. Can take 45, 256 minus 5 minus 1, 4. So let's take these values. So we'll do the same test. So if we do print id of array 0, let's take 0. It says 12128. Now if we check, let's duplicate this. Actually we need to duplicate. If we check array, the same thing, we will check for the second one, 0 1. It is still the same, which is interesting. 2544. Is it 356? Wait, let me check the fourth one. 0 1 2 3. So I think this threshold is still lower. I think it's slightly higher, maybe probably 356 or something, probably not 256. But if we check 4000, 0 and 1, still the same. Okay. Strange. Is it because it's in contiguous locations? 0 2, still the same. This actually should not happen, but if I'm not wrong, I think it was 256. Anything beyond this value ideally doesn't. So let's take, suppose, 10 and minus 10 once again. 0 1 2 3 4 5 6 5 and 6. They both are same locations. Okay. Yeah, 5. Give me a moment. Array 5. I guess. Okay. Not within the same array. It should be within different array. I guess I was taking the same array. Same array it reuses. If I take a different array, and if I use the same set of, since the values are essentially the same, right? We would think that the memory location would be the same, but it is still the same. Oh, okay. Okay, I think I will clarify this in a different class. This should ideally not work, but seems to be referring the same memory location, which I'm not sure why it's doing that. Okay, so let's move on. Ideally this should not work, but it seems to be matching the same memory location for some reason. Let's try printing id array, maybe like the fourth value. What? Something's wrong. Okay, something is wrong. Let me do one thing. Let me restart the kernel. Something is wrong. It's pointing this as well to the same memory location. I am not sure why it's doing that. Yeah, this should not happen. Let me restart the kernel. Okay, I will get back on this one. This is acting strangely. Actually, they should not. If the values go beyond 256, it automatically, Numpy automatically creates new memory. It allocates new memory locations. Because if you see, this is acting pretty strange. I don't know if I'm doing something wrong here, but even for array 4, element 4, which is 0, 1, 2, 3, 4, even 256, it's pointing to the same memory location, which is very weird. Okay, I will we'll discuss this later on. So that is basically all there is about copy, shallow copy versus deep copy. Yeah, so let's jump to the next topic, which is array splitting. So the idea of array splitting is you want to divide a single array into multiple subarrays. So the syntax is np.split. So the syntax is np.split. So let's look at the documentation. So we pass in the array that we want to split, and then indices or sections. So what this does is, so what this takes is, it takes two types of arguments. One is if you pass a static scalar value, like just a number. Let's say I want to split this array into two different or three equal sections. Let me just show that in so if I have an array, say 1, 2, 3, 4, 5, 6, and I want to split this in two equal sections. So I just have to pass np.split. I pass this array, and I want to, what is this called, indices or sections. Indices or sections, I set the value to 2. This then divides this into two subarrays. If I pass indices or sections, so this is the sections part. Now if I pass the indices, so if I do np.split, I pass the array, and if I pass indices or sections, we can actually pass a ascending or sorted array of in list of indices. So if I say I want to split this array at index 0, 1, so 0, 1, 2, 3, 4, 5, I want to split it at index 1, I want to split it at index 3, right? I pass index 1 comma 3. What happens is this then splits this list into, you will have list 1, then you will have list 2 comma 3, 2 comma 3, then you will have the other list 4 comma 5 comma 6. That's how you can split this. That's how split works. Let's look at the functionality. Say array equal to np dot a range. Let's take 9 elements. Then we do an np dot split. We pass the array, and let's say we divide. Let's divide this. So since it's 9. I'm not sure. I think yeah. Let's try to split this into 2 sections. Let's see what the output will be. You see, it's throwing a value. Array split does not result in an equal division. So we have to provide the if we are trying to divide it into equal divisions, we have to provide appropriate number according to the number of elements that are present. So let's try 3. If we do 3, these are splitting into 3 equal divisions. So if we want to split it into 2 equal divisions, then we have to do 8 elements, then we get 4 and 4, right? So that is splitting with what is that? Indices or sections. There is no, okay, I think what is the, okay, R sections. So that is the sections part. Now if we look at, let's try the same with indices. So I pass in a list of sorted. So it has to be sorted integers. Is an integer n will be divided into n equal arrays. This is the first one. It's a 1D array of sorted integers, right? So let's divide 8 elements into, maybe I want to divide this at index 3, at index 6, and at maybe at index 8 as well. Let's see what happens. So you see, it divided 0, 1, 2. So let's print the original array first. I think that will. So this is our original array. So it took 0, 1, 2. So at third index, so how it is doing it. So if we take this side, if we take the example of 0, 1, 2, 3, 4, 5, 6, 7. So if we split it at index 3, okay, so yeah, this is going from 0, 1 to 3. So index 3 would be this, 0, 1 to 3. This is the index 3. Then index 6. Index 8, there is no 8, right? There is no 8. So if we are splitting at 3, it is taking from 0 to 3. The range is 0 to 3, 3 is excluded, which will be 0, 1, 2. Then it is going from 3 to 6. 6 is excluded, so it's going 3, 4, 5. Then it's going from 6 to 8. 8 is actually missing. So what is it giving? 6 and 7, right? Now since 8 is missing, it is just giving us, returning an empty array. No, wait, is it returning empty array? Wait. It is returning an empty array. So suppose we ask for more, let's say index 10 as well. So you see here, At index, there is no index 8, so it's giving an empty array at index 8. There is no index 10, so it's giving an empty array at index 10. So that's how split works. Split also has an axis, if I'm not wrong. It has an axis. So let's take a 2D example. 2D array split. Let's take 9, reshape. 3, 3. So we have our 2D array, and if we are trying to split this, pass the array. Let's take the same example, and I set it to axis. Let's do a horizontal axis, which is axis 1. Numpy ND array object has no attribute split. Oh, sorry. Okay, so we have np.split. So if you see here, what is it giving? It is giving 0, 1, 2. What is the original array? Then it's giving a strange value. Let's look at wait, first let's try to split this into 3 blocks. If we split it 3 along the horizontal axis, if you see here, it's cutting it into 3 equal blocks. So first column, second column, third column. We set it to axis 0, which is vertical axis. We get our rows as the subarrays. Now this thing is curious. Let's try to split it at index. Okay, that makes sense. So at index 3, what is index 3 here? 0, 1, 2. There is no index 3 here, right? There is no index 3, so it returned the entire thing, and then third it gave empty array, sixth it gave empty array, eighth it gave empty array, and 10th also it gave empty array. So let's try to give some reasonable values. So if I give at split at 2, at index 2, just one value, index 2, and let's say 4. So you see here, along axis 1, which is horizontal axis, 0, 1, 2. So it took till here. First 2 columns it took, and then it returned the third column, which is the other one, and then since there is no fourth index, it gave an empty array. So the thing to remember is the result of a split, especially when it's index, when you are doing with indices, the result of a split is equal to number of the indices or sections plus 1. Why do you think we have plus 1? Because if you see here, let's take a smaller example. I think that will be easier. We'll do it at 3 and 6. So you see here, we have the original array at 0 to 7, and we are splitting at section index 3, which is over here. So we have 0, 1, 2, that's 1. Section 6, index 6. Then we have 3, 4, 5. So length of this list, which is 2, then plus 1, which is the remaining the remaining list that is present. So that's how many number of sub arrays that you will be getting as the result. So that's about splitting. That's all there is to splitting. You can do this vertically, horizontally. We have discussed the axis. We can the other yeah, that's all there is to splitting. Let's go to stacking. Array stacking. So stacking, like I said in the beginning, it's about joining multiple arrays. If you want to group multiple arrays into a single array, we can use stacking. The syntax is array. So the okay. I guess I forgot one thing. So just like np.split, there are two more methods which are actually unnecessary if you know np.split, which is basically np.hsplit and np.vsplit. These are basically extra syntax. It's not really necessary because we can already do the same operations with np.split. But since these are there, let me just explain anyway. So this is actually the functionality is the same. You just don't have to specify the access. So if you look at the documentation, so you pass in the array, you pass in the indices. You don't have to pass the access because this is particular to horizontal split. So let's take the simplest example. It is completely the same. Instead of split, we'll do an edge split, and if you see, it split the thing into two different sections. You can pass in the indices as well here. Say 2, 4. It splits that thing horizontally. Okay. Now, we since this is 2D, the axis is meant for 2D. Let's take a 2D array. Okay, where is it? This one. Let's take a 2D array, and you see the result remains the same. Or you can do a v-split, and it divides vertically, right? So that's all there is to splitting. Similarly, in array stacking, you have three methods. If you know one of them, I think it's more than sufficient. But concatenate, this actually covers all the scenarios. But there's also extra sugar like np.hstack, and you have np.vstack. So np.concatenate. Let's look at the documentation. It takes two arguments. It's pass in. So it essentially accepts a list of arrays, or a tuple of arrays, or and then we can pass the access as well. The other arguments are not so necessary right now. We'll just be looking at these two. Let's create some arrays right now. Let's say array equal to np.arange. Let's take 3 of them. Two, 3. If I pass array 1, array array 3, and if I don't specify any axis. So you see here it merged the entire um, list. Okay. I guess I'll have to look into the other parameter as well. D type. There supposed to be one more. 1 second. Custom. So okay. So if I set access as, I think the default it takes to access as none or access 0. Okay. What if I set access as none? There is no access one, obviously. So 1D array. Actually, there is an option called none for something. I'm kind of forgetting. Is it data type none? Out none? What is? If provided the destination to place the result, the shape must be correct, matching that of what concatenate would have returned if no out argument were specified. Shape must be correct. Shape. Dot concatenate. Okay, let's take reshape. Let's take 2D array once. If I do not specify the access, I think it's still access 0. Okay. I guess I have a slightly hazy memory there. So yeah, this is basically, it just stacks the arrays vertically and horizontally. I was thinking there was one more parameter which has a none option, where concatenate basically flattens even the 2D. If you give a 2D list and if you don't specify that parameter, it essentially flattens the 2D list into 1D list. I thought that was access, but oh, it is access. Okay, type is none. Yep. So let's look at the 1D array option first. One D array concat, or let's call it stack. And we do this we don't even have to specify any access. Concatenate basically takes all the elements from each list and just places it one after the other. And if we do a 2D if we take a 2D stack, if we do 2D stacking, and if I set the access to none, it essentially flattens the 2D array list into 1D array list, and then stacks one after the other. If I set the access to 1, which is horizontal stacking, then if you see 0, 1, 2, 3, 4, 5, 6, 7, 8, so each matrix is stacked one after the other. And if I change it to access 0, it is stacked one below the other. That is basically all there is to stacking. One important note is you cannot have the shape of the arrays must be the same. You cannot have some arbitrary shape. So suppose let's take the example. See, let's call it 2, 3 and so cannot reshape array of size 9 into shape 2 comma new axis. Okay, 1 second. Is it because of this? Okay, that's 9. That's 3 into 3. So let's take it 8. I think 8 will have slightly more flexibility. Let's keep it 4. So we have 4 cross 2, and this is 2 cross 4 and 4 cross 2. If we try to concatenate, it will throw an error. All the input array dimensions except for the concatenation axis must match exactly along dimension 1. So since dimension 1, so I don't know if I have already said this, but basically axis 0 is first axis. It's also called as first axis. Axis is 1 is called second axis. So when they say along dimension 1, what they mean is first axis. 1 is first axis, so it is axis 0. So the array at index 0 has size 2 and the array at index 1 has size 4. Has size 2. So it is 4 cross 2, and this one is 2 cross 4. So the when we are trying to stack it along the axis 0 is vertical axis, we need to make sure all of them have 4 rows and 2 columns. So we change it to 4. It then stacks properly. There is one more. There is actually a condition. Let me think. So the conditions are exactly the if you are extending it along axis 0, along axis 0, which is vertically, then the then the number of columns must match the total columns present overall. Okay, I'm not sure if I'm explaining this properly. Let me see. Columns. So axis 0 is vertical. Let's say I'm giving I don't know if this is allowed. It is still allowed. Okay, so the conditions are if we are going along axis 0, axis 1. So suppose it's axis 1 which is horizontally, then the then the rows must be exactly the same size as the largest array, and columns can be any number of columns. So it has to be rows comma n columns, and if it is axis 0 which is vertically, then you can have n number of rows, but you should have exactly the number of columns that the largest array has. Suppose let's try to implement this one. So we're currently on axis 0 and we are vertical, so n rows. So yeah, n number of rows and same column. So yep, that's exactly what we did here. You can have any, let's try to take this as 12 elements. This is 24 elements. So as you can see, the shapes are significantly different here. We have a 2, 4, we have a 6, 4, and we have a 3, 4. As long as the columns are all the same, you can have any number of rows, and it will automatically it will still perform the operation, stacking operation. The same applies to if we switch it to axis 1, that will throw an error. So for axis 1, you need the reverse. You need this as 4, minus 1. You need the same number of rows in every array, but you can have any number of columns. Then the stacking operation becomes successful. So that is all there is to array stacking. Thank you, and I'll see you in the next one.